Hey there, physics enthusiasts. Welcome back to our channel. Today we're delving deeper into the realm of motion with a focus on displacement time and velocity time graphs. Whether you're preparing for your A-level exams or simply intrigued by the wonders of physics, you're in for an enlightening ride. So let's kick things off with displacement time graphs. So picture this, or look at these graphs I've got over here. You're tracking the movement of an object graphically with the displacement or change in position, right? How much you've dissed from the place on the vertical axis, and on the horizontal axis, you have time. So as the object moves, we're marking its displacement at different times, at time intervals, creating a graph that illustrates how position has changed over time. Now, what can we glean from these types of graphs? Well, let me get the little penaroo. A horizontal line on a displacement time graph, well, the displacement isn't changing over time. It's not dissing from the place over time. That's going to represent an object which is stationary, which is not moving. A line which is sloping upwards here that has a gradient means the object is moving in a positive direction. So over time, it is displacing in a positive direction. Cool. So that's implying to us it has a velocity in the positive. If we were to have something like this, it is a downward slope. It's indicating it's moving in the negative direction. This one here, well, it's clearly moving in the positive direction, but it's increasingly, the rate it's moving in the positive direction is increasing. So this right here is a positively accelerating object. So that's kind of talking about the shapes, but we're not in the mindset of memorizing or internalizing shapes here. We're trying to build up systems. We're trying to build up modalities of thinking that we can apply to any graph, and not exclusively displacement time graphs. So what we're going to have to do for that is we're going to fall back to, okay, we're talking about gradients here. What is a gradient? How do I calculate a gradient? What is the gradient of this graph? And what is the gradient in the context of this graph based on its axes? So as we know, change in y over change in x gives us our gradient, of course, being represented by m in the old function of a straight line graph, y equals mx plus c. So in this graph, what is the change in y? Well, the y in this graph is displacement. Okay, in this graph, what is the change in x? Let's contextualize this graph. Well, the change in x is time. Change in displacement over change in time, that's going to give me the velocity. So the gradient for these graphs is velocity. So with that in mind, let's revisit these and let's, apply that system of thinking. Yeah, okay. This, remember, talking about the gradient of a graph, you can do for any graph, even if you don't understand what the axes mean. I can look at this, forget that it says displacement in time. I can look at that, and every single time I can look at that and say that has no gradient. All right, that has no gradient. I can then look at the axes, and in this case, I do understand them. I know displacement over time gives me velocity, so I know that this first graph has no gradient, no velocity, stationary. Full rep of thinking every single time. Build up these modalities of thinking. You can apply to any graph in the future. Next one I've got here. This one does have a gradient. I've got a positive gradient. I've got a plus m value. Okay, positive gradient. In this context, gradient means velocity. Positive velocity. Positive constant gradient. In this context, the gradient means velocity. Positive constant velocity. See this kind of system, it never fails you. And you might be thinking, okay, I don't need to do that for these graphs. You probably don't, right? You probably don't. But we're trying to build up systems of thinking that we can use in the future for, more challenging things in your A-level course, your IB course, whatever your high school course or college course is, and further. We're thinking big time here. We're not just thinking about passing an exam. We're thinking about getting good at physics, and as a consequence, you pass exams, not just trying to get good at exams, right? This one here, start off with low gradient, increasing gradient. Okay, so this graph has an increasing gradient. Now let's look at the context of the gradient. The gradient is velocity. So, increasing gradient is velocity, increasing velocity, acceleration. Boom, right? So I've got an increasing positive gradient. The gradient means velocity. That means I've got an increasing positive velocity. That means positively accelerating, right? Just apply this thinking, do the full rep, right? It's not like these people doing squats who are just bouncing up and down. No. You do the full range of motion, all of the thinking every time, full range of motion for every single thought, no matter how basic. And then you'll be able to do those full reps just like that. And then you'll be able to take that to unknown situations and apply it. That's the trick, man. That's the trick. Getting these new ways of thinking in your head instead of just memorizing. Then you can invent the facts. You can work out the facts instead of being at the mercy of, do I remember it? Was it curvy means this or curvy means that? Sounds like a coin flip to me. And also, doesn't really sound like great personal development of your thinking in your mind, remembering stuff. I don't know. Okay, so now let's shift focus to velocity time graphs. Instead of plotting displacement against time, we're plotting velocity against time. All right? Velocity, of course, being the rate of change of displacement, which we reaffirmed when we were establishing the gradient of the displacement time graphs. So on the vertical axis, we have velocity. On the horizontal axis, we still have time. As the object accelerates, decelerates, or maintains constant velocity, we mark its velocity at different time intervals along the graph and produce something like this. Okay, so same thing again. Let's contextualize the gradient. Gradients change in y with change in x. In this graph, the change of y is the change in velocity. In this graph, the change of x is the change of time. So in this graph, the gradient represents acceleration. So I don't have to remember what the gradient is in a velocity time graph. I can just work it out every time by doing the full rep, right? So let's apply it to a bunch of different graphs. So here we go. This top graph here, gradient is 0, meaning acceleration is 0. So if acceleration is 0, it's either stationary or it is moving at a constant speed. Which is it going to be? Well, it has a v value. It has a non-zero y-intercept. Yeah, it's constantly whatever this velocity is. So that one there, uniform motion, constant velocity. Next one, gradient is constantly positive, meaning acceleration is constantly positive. Uniformly accelerated motion. Next one, my gradient is a constant negative value. All right, so what's that mean? That means that the acceleration is constantly negative. Maybe that's 9.81, right? Maybe that's representing something in free fall. Yeah, and that gradient there is minus 9.81, average gravitational field strength of Earth. Maybe that's that. Next one here, I start off with a low gradient and I go to a high gradient. Okay, so gradient is increasing. Gradient represents acceleration. So what have I got there? I've got an increasing acceleration. I've got jerk. Yeah, I got the next derivative of displacement in time. I've got jerk. Right? So that's how we interpret these. But with the velocity time graphs, there's another trick. Okay? So when we're looking at graphs, there's a few things we want to be paying attention to. Now, we've already established that the gradient is something really, really important to pay attention to. What is the gradient? How does the gradient apply? Is the gradient important? Another thing, that the next trick we're going to be talking about, which we want to take note of, is the area under the graph as the next sort of concept. So let's have a look at this here. So here we've got speed. Let's say this is velocity. All right, let's keep this vectors for right now. So we've got a velocity time graph here with a constant gradient. Gradient represents the acceleration. So I know this is constantly accelerating. Now, there's something else though I can learn from this, and that's by considering the area under the graph, the area under the curve, the area under the line, however that's presented. Okay, so let's think about the shape here. Yeah, so it's a triangle for this one. So that right there is the height. That's the base. Right angle triangle, area triangle, half base times height. Well, let's contextualize this. Okay, what is the height? The height is velocity. What is the base? Time. What's velocity times time? Displacement. Yeah, we know that from this. And if you've forgotten that, you can just get it from the units, man. Meters per second velocity times by second time leaves me with the unit of meters. I've got the directional component from the velocity. So what's something that has direction is measured in meters? Displacement. So even these most basic equations you don't even need to know, man, because you can just like work them out again. So there's another thing that we can be gleaning in from the velocity time graphs. The area under the graph is significant because it is showing the displacement of that journey. So when we're playing around with graphs, we want to be thinking about area under the graph, what's the significance of that, and work it out. Do the full rep, just work it out. And gradient, what's the gradient significance? Do the full rep, work that out. Don't remember this stuff, work it out every time. You'll be able to do it so rapidly, and it'll build up that modality of thinking like I've been trying to stress to you guys. So there we go, displacement time and velocity time graphs, powerful tools for analyzing motion and gaining deeper insights into the behavior of objects. By mastering these concepts, you'll be equipped to tackle complex problems and unravel the mysteries of motion. Ooh. And that wraps up today's lesson. I hope you found it informative. Keep exploring, stay curious, and remember the world of physics is full of wonders waiting for you to be discovered. If you haven't already subscribed, I'd really appreciate it. If you've got any comments on this video or things that you'd like to see covered, please shout out below, or even just a little thank you message. And if you check out the description as well, I've got links to all of my other socials where I'm posting physics stuff and resources you can download and whatever. So until next time, bye.